So in foundation design, we have two issues. The first one is how to size the footing. You know that at the bottom of each column, usually you're going to have a footing or a wall. You need to have a wall footing or a pad. You need to have a pad there to take the force from the structure to the soil. So the first problem here is going to be how to come up with the size of the foundation or the pad. Size meaning length by width. Second problem is going to be the thickness and the reinforcing, the concrete strength, and so forth. Are you guys here with me? So we're going to have here two issues. One of them is how to size the footing. The second one, how to size the reinforcing and the thickness and everything inside the footing itself. So generally speaking, this foundation will be supporting gravity and non-gravity columns. What is gravity columns? Gravity columns is given those columns or walls supporting dead load and life load. This is what we call here gravity. Gravity means weight of things. So it's going to be gravity of the dead load and gravity of life load. Non-gravity means columns or members or walls exposed to seismic forces like earthquake forces or wind forces. So we call non-gravity. We call it also lateral loads. So this lateral loads and moments, right? This lateral load and moments is going to be either due to, say here, seismic, which means earthquake loads, or wind forces. This is going to be the lateral loads. The gravity means what? Again, I'm going to put it here. I'm going to say dead load or life load weight. So, okay. There is a difference in the way that you design member supporting gravity versus member supporting seismic and wind forces. It's not the first time to look at this picture here. We have looked at it before when we were talking about the columns and the load path. Then we said that the load is going to be coming from the joist, the slab to the joist, and then after that to the column from that level, which we called here the second floor, and then goes down. So this column here supports the column above and support this slab or this level. And then the force is going to continue coming down, and here you're going to have the first floor concrete slab. All the loads going to be going to this column. Now this column here supports everything above, which means this column supports whatever load that this column supports plus the load coming to it from the first floor. At the end, you cannot just put the column in the soil. If you put this column in the soil, the column just going to be penetrating the soil. The soil wouldn't have any resistance. And this reason is going to happen. I mean, the reason that this happens because the soil bearing pressure is going to be very small, the allowable bearing pressure. So once you put the item on it, excuse me, once you put a heavy item on it or a column loaded with heavy loads like the way that you're looking here at, it's just going to penetrate. So you need to have a footing here. Otherwise, this column is going to be penetrating the soil. Also, you need to have this footing to be able to make this member here stable. You cannot just have it like a column here that sits on the floor or on the ground, on the soil, without having dimensions like length by width. The problem is going to happen if you don't have it. Again, column is going to be penetrating the soil. So I'm going to say, how about this slab and grade? Would you consider this to be foundation? You say, yeah, it's kind of foundation because you can have here some dead load and life load that you put on this slab and grade, and the slab and grade is totally supported by the soil. And it is extended in both directions. Let's say in this direction, I'm going to call this the X, and the Y direction is going to be just extended. So if you put any weights here, it's going to be transferred to the slab and grade, and then after that goes to the soil. But whatever load that you put here is going to be uniformly distributed on the slab and grade. So you don't expect here that slab and grade, because the load on the top of it is going to be penetrating the soil. Now here you take the load from the entire slab and then you concentrate it in a column. So now the load is going to be inside the column. Which means if you like to compare here between the load that goes between the slab and grade and the soil per square foot, compare it to that you have on the column per square foot of the cross-sectional area of the column, I'm gonna say here is gonna be extremely very low compared to that force on the column. This is the reason that you put lots of load in a very small area, which is a column section. Therefore, the pressure right below the column, this provides that I don't have here any footing, the pressure is gonna be so high that the soil won't be able to support it. So now I understand that the soil has certain maximum allowable pressure that you can put on the top of it. So here, I'm gonna put here the force is gonna be going to the column. And then after that is gonna be going to the footing. And then from the footing, by contact with the soil, is gonna be going through it. If you know the length of this footing, so I'm gonna say L. And you know the width of this footing, I'm gonna say B. And the column load that goes to it, so I'm gonna call it here P. P is gonna be the column vertical load. Now this column here, again, supported now by a pad that has a cross-section area of, so I'm gonna say here, area of the footing, contact area, if you like to call it this way. It's gonna be equal to L times B. This is gonna be the contact area. This is gonna be between what? The soil and the footing. The question is, now once I have this contact area, how much pressure that you have between the soil and the footing? Let's say the soil pressure. I'm gonna call it here soil pressure. Is this allowable? No, this is the action. Because now we have an axial load that's gonna be called P acting on this pad. So we're gonna say the soil pressure, I'm gonna call it here Q, lowercase. Usually this is gonna be the term that we usually use, the symbol. Is gonna be equal to P divided by A. So the soil pressure that you have now below the footing is gonna be equal to Q. Again, now this is gonna be simple footing. And this simple footing is supporting this axial load. It's gonna have here a soil pressure of Q. This Q here, we need to be sure it's gonna be within the allowable. So the soil engineer is gonna come to us and say, the allowable soil pressure that you can use in this location within this site is gonna be this much. So let's say, now who's gonna put here Q allowable? Q is gonna be Q sub, this is supposed to be sub allowable like this, right? It's gonna be equal to, and then he's gonna give us some value. For example, I'm gonna say, let's say 3,000 PSF, which means each square foot of the soil is gonna be able to take up to 3,000 pounds. Now, what's gonna happen if you put higher pressure than the 3,000? You're gonna say more sediment is gonna happen.
Professor, this is
Yes.
Q allowable is dependent on the soil, correct?
Yes, this is soil property. This is why it's gonna be, yeah. So this is why the soil engineer is gonna give it to us. So we're gonna say this allowable soil pressure, right? Given to us by whom? Geotechnical engineer. So the geotechnical engineer is going to give us the allowable soil pressure. As a structural engineer, I don't come up with it. So soil engineer is going to be taking soil samples, take it to the lab, he's going to do some analysis, right? And then he's going to be developing a report that we call geotechnical report. So I'm going to say here through some report or soils report. You can also call soils report, right?
Mm-hmm.
And in the soils report, he's going to say how much is allowable soil pressure. Have you guys ever seen a soils report in your life? Or no?
Yes. Yep.
Okay. Have you guys seen it? Who has seen it? Who has seen the soil report?
I've not seen it before.
You have not, or you have?
Haven't.
You have not. Okay.
I did.
No problem. If you haven't seen it, this is fine. I mean, there's nothing wrong with this. There's nothing wrong at all with this. Give me a second. Have you guys all taken soil mechanics?
No.
Yes.
Yes.
Yeah.
Has anyone didn't
No.
take soil mechanics yet?
In it right now.
Oh, you are taking it right now. Did you guys talk about the soil bearing pressure yet? I'm sure you should have, right?
Yeah.
Okay, give me a second. Okay. So for me as a structural engineer, I don't develop the soils report. I don't go there. I don't take samples. But people work in the geotechnical engineering field. This is what they do. This is their business. Let me show you here something real quick. Here's a soils report developed for a site.
I can't see it if you
Yeah,
can
we
share it.
can't see.
Yeah. I'm gonna jump to a certain page. I don't
Oh,
wanna.
okay. Gotcha.
Gotcha.
Yeah, I'm coming. I've been looking for it and then I find it finally. So this report, the one I have here is about 70 pages. And give you lots of information about the site, about the analysis, about seismicity of the place. Look at this. Conventional spread and or continuous ring wall footing may be designed using an allowable bearing pressure of 2000 psi. And then they give more discussion here, and it can go up to a maximum of this much if you use seismic. And then you have also this 18-inch minimum and 24-inch, and you have more information here. So this section is called foundation or foundation design. And here's the slab on grade. They say, what is a slab on grade? It's gonna be, this is a slab on grade, right? They say, well, it needs to be minimum of 5-inch, and they recommend certain amount of reinforcing there, like number 4 at 18 inch on center, each direction in the mid height of the slab. So what's important to me when I open this soils report is to look for this section about the foundation design. I'm gonna say here, look at this. Allowable soil bearing pressure of 2000 psi. So you see it's gonna be allowable, right? So what does it mean by allowable for you? Does it mean a trend design or ASD design? I'd like to hear from you guys.
Is it site specific, specifically to the soil
Yeah,
that
it's specific to that
building?
location, only for this location, which means each building you can have different soils report. And if you have a very large site, you can have different parameters. You can have different soil bearing from allocation to allocation if the site is really large. But my question to you is this an ASD design or LRFD design? You guys know the difference between ASD and LRFD, right? You know.
No, I don't know it.
Okay. You guys are aware of this load combinations, right? This is gonna be what? Load resistance factor, which means strength design. When you have these factors here, 1.4, 1.2, 1.6, it means that you're using a strength design, right?
Mm-hmm.
Right. This is the LRFD. So when you do concrete design, you do it what? LRFD or strength. I prefer to call it strength. Now the question is, when you do, this is the other question, when you do like soil bearing, and then it says here allowable, are you using LRFD? Are you using the same load combinations? And can say no, we're gonna be using different load combinations, right?
Mm-hmm.
So I'm gonna put here the ASD design. You guys hear about ASD and trends or LRFD, right? So the code itself, it has some load combinations here when it comes to ASD. And this one you say here allowable. So once you see here the word allowable soil bearing pressure or soil pressure, it means you're gonna be working with allowable strength design. You don't really do strength design like the concrete design we do. And look at this load combinations. Are they different from the ones we used to? You can say, here's the one that you're used to. It says 1.4 times dead load versus 1.2 dead plus 1.6 live. Look at this here. It just says dead load. There's no load factors, right? We don't have load factors. Dead plus live, you just add the forces to each other. You don't multiply by anything, and then you compare them to some allowable value. This is not what we do when we do concrete design. You guys agree? In concrete design, what we do, we multiply by load factors, and then we use phi mn or phi vn or phi pn. So we have, this is here what we call strength design. Strength design, what do you have? This is taken from different course, but it has the same thing. In ASD, you have an allowable, right? And then you have your demand. In LRFD, you have your demand is called M sub U, and your strength is gonna be phi man. It's completely different. So when you do here size of the pad, like the discussion that I'm going through here, this is going to be ASD design. So I'm going to say when you do soil design is going to be ASD. Now someone's going to say, never heard this term before, soil design. Well, it's actually called foundation design, and then I'm going to call it here, which means soil, when you work with the soil itself. So I'm going to say footing or foundation, footing size. What does it mean by size? Size can be L and B. It is not really about the thickness and the reinforcing. Thickness and reinforcing, now we're going to be talking about concrete member design, which we're covering this course. But now, since I'm going to be talking about foundation design, I need also to address this footing size. So footing size is going to be ASD, allowable strength design. You just need to add the load. There's no load factors. And with this, you can find out the size of the footing. What's the purpose of doing the size of the footing? To be able that the soil pressure, which is right below the footing. Now, what is the soil pressure again? Which is Q, which is equal to the vertical load divided by the contact area between the footing and the soil, is not going beyond the allowable value, the Q allowable. Okay, so I'm going to call this footing size, which is soil, kind of soil design, if you like, is going to be ASD. How about the footing itself? What do you mean by the footing? The footing itself as a concrete member, which means depth, reinforcing, concrete properties, the material, and the whole thing, like the design. I'm going to say this is going to be strength, like the way we used to do it, which means in this case, I should expect phi mn for the footing. I also should expect phi vn, because you're going to be doing here shear check, and you're going to be doing flexure check on the reinforcing that you put at the bottom of the footing. Same thing, same footing. You have round column or you have rectangular column. At the end, you're going to have a pad or a column at the bottom. So when you have a pad like this, it's going to be, let's say, 4 feet by 4 feet, 3 feet by 3 feet, maybe 10 feet or 12 feet by 12 feet. It could be also rectangular in shape. It could be also maybe, let's say, 10 feet by 20 feet, but just support a column. In this case, I may call it spread footing or a pad. So in this case, you may call it here spread footing or a pad, also named pad. It's like a piece of concrete. But if you have a big foundation here that supports everything in the building, we're going to call it here mat foundation. Here's the way you split mat foundation. What is mat foundation? It's going to be a big footing support all the columns in your building. Of course, it's going to have different design. This here, if you look here at this footing, it's going to be like a strip footing. Whenever you are going to have a wall, you're going to have a footing right below it. So in this case, we call it wall footing. This also is going to be wall footing. You see, extended. What is mat foundation? Do you see here any mat foundation in this picture? I'm going to say no. Mat foundation is going to be a big, thick concrete slab that sits on the soil, and then it has all the columns going to it.
Are residential homes mostly mat foundations then?
No, the residential, the one that, let's say in the house, is going to be like just a slab on grade mostly, or it's going to be raised framing. Like sometimes you call it raised foundation. It's not really raised foundation. It should be called raised
That's where you have a
framing.
crawl space underneath, right?
Exactly. So we call this raised framing. But people used to say raised foundation, which is incorrect. Foundation is going to be down below, and then the first floor is going to be raised. It's going to be right here, right? This mat foundation is different. Mat foundation, when you have concrete building and you have columns or steel building, and then you have very big mat, like thick slab, it can go maybe 3 foot thick, right? It's going to be 3 foot thick, or maybe 10 feet, not 10 feet, 5 feet thick, the maximum that I have designed, maybe 5 feet thick. And then you have all the columns sits on it. But this concrete slab, usually in residential, is going to be 4 inches. Sometimes you do 3.5 inches. I don't like it. In many cases, usually we'd like to go to 5 inches. Same thing. So the footing here is going to be supporting columns. We call this spread footing or a pad. And here's a picture for one footing. You see here, it looks like straight edges, but this is a reality. This is the way that they do it. Because if you're doing a hole here in the floor or on the ground, right, you don't want to put a formwork. To put a formwork is going to be expensive. So what they do, instead of having straight edges, they just do a larger opening a little bit. So this hole is going to be a little bit larger than the size that you're given in the drawings. So let's say you give him 4 feet by 4 feet. You're going to say, you know what, it is cheaper that I'm going to make it here 5 feet by 5 feet. I'm going to get you here some extra concrete on the perimeter, then just put some formwork, which is fine with us. I mean, as long as you have enough cover. What is a cover? Cover means the clear spacing between the soil and between the rebars, then you should be fine. And here's a pad. It has bottom reinforcing and top reinforcing. Have also some column dowels. So this rebars, this is what we call here column dowels. This to provide continuity between the footing and between the column.
Professor, what are
questions?
dowels? So, like, could you explain a little bit more? Because for dowels, what are they? I'm kind of confused. So they're just continuations to connect with other, like a column that would be placed right there.
You know that the column also has some rebars inside it, right? That we have seen in the column design section, right? So it has lots of stuff. It has rebars going through it and it has ties. So now you need to connect between the footing itself and between the column, right? So you need to connect them with rebars. So this is gonna be the rebars that you put first when you are putting the concrete for the footing.
Oh, so they're left exposed, and then you kind of create the formwork around it, right?
And yeah, and then after this, first before you do the formwork, you start to put the splice and then put the rebars for the column itself above the footing. And then after that, you put the form around it, and then you pour the concrete inside the column. Because you cannot pour the footing at the same time with the column. It's gonna be too much, right? So you can do a cold joint here. This is what we call cold joint. Cold joint means that you do the first pour, and then you roughen the surface of the interface between the column and the footing, and then you pour the column after that. So we call it cold joint.
Thank you.
Some pictures from actual, no problem. Some pictures from actual project that we're doing. There's gonna be here some wall footing. As you see here, you have lots of dowels. This is what you hear, dowels. So all of the 3 bars is gonna be sticking up, and then after that we put the concrete wall around it, and then we pour. First we pour the footing, right? And after we put it, we start to put the block wall, because this is actually concrete masonry wall. It's gonna be above it. So here's the footing, no rebars yet. Now you put the rebars, and then you put the dowels. It's gonna be sticking up. And then once you put the blocks, after this, you're gonna be doing the splicing of the rebars. You continue the rebars like this. So another rebar is gonna come right next to this. It's gonna be going all the way to the top of the wall. So you call this a splice. So this piece here, the splice means the length, or the fact that you're putting 2 rebars next to each other. And we call this a dowel, this piece of rebar that sticks up. Another big footing, is from a project that we have done in the past. And you see the footing is really big, just one pad, and you see how thick. Actually, you can call this a mat, because the thickness was about 2 feet and 6 inches. And then after that, it has a structure sitting on the top of it. The structure is called the flare. And here's the flare, and here's the pad, the big mat here, if you like. And the height of this guy here is about 60 feet, and the weight was about 80 kips, 80,000 pounds. And then you anchor it, and this to burn the methane gas. So, design for this concrete foundation is not really tough, because by now you have learned how to do flexure design, which means you know how to figure out the amount of reinforcing, and you know how to do the shear check on the beams, So what we're going to be doing here, we're going to be extending our knowledge to foundation design. In this example, it says gravity reinforced concrete footing. It's going to be 8.6 by 8.6 by 2.6 inch deep. supports a 24-inch by 24-inch rectangular reinforced column. So the column is going to be square, is going to be sitting on the top of this footing. Concrete strength is going to be 3,000 psi, and the column ultimate axial load is equal to. Let me just cross this out. It's going to be 680 kips. So it's going to be the total load. So I'm going to say, it says here gravity, which means dead load and live load. So I'm going to say this number that you're here looking at, 680, is going to be actually dead load plus live load. Just give it to me. This is very similar when you have a member or a column, then we say ultimate load is going to be 680, which means factor are included already there. Now in this case, it's going to be dead load and live load, total of 680. The flexure reinforcement of the footing is most likely. So now I have everything about the footing. I'm not doing here sizing of the footing yet because it is given to me. So I don't really need to reinvent the wheel here and say how much is the soil pressure. It is given to me already, but it says that you have this axial load of 680. So okay. And unfortunately, in this case, I don't know how much is dead load on live load because, you know, if you're sizing the footing, you do ASD, you just add the two loads to each other. But when you do here LRFD, right, you need to have ultimate load. So let's read this again and just confirm what we're reading. It says the column ultimate axial load. Axial load meaning what? Just dead load on live load? You can say no. This is going to be P ultimate, which is equal to some factor. I'm going to say maybe 1.2 dead load plus 1.6 live load. So this number here is given to me as an ultimate load, not a service load. It says the ultimate axial load. Am I correct? We need to be careful here what we're reading. So ultimate axial load, again, 680 kips. So I don't really need to know the dead load separate and live load because it is already factored for me. You can say, okay, this is good. I'm gonna take you back here a couple of slides to this slide here. When it says this speed that we used to work with, that was service load, which means dead load on live load. And this soil pressure was at ASD. It was at service load. So now I'm bringing here a new term to you. So what does it mean by ASD? You can say ASD means what? Anyone recalls what I've just said? Service loads. So what are the service loads? Service load means dead load and live load, which means load combinations according to ASD. What is ASD? Allowable stress design. It's going to be right here. So this load here, when you add them to each other, which means this one, when you add them to each other and use this load combination, we call this service load. So I'm going to put this here. Say this is going to be called service loads. I'm going to put it here so that it can stand out. You can see this ASD is going to be service load. How about this load here? Do we call service? You can say no, we call this ultimate load, right? Call this ultimate load. So now we understand the difference between ultimate load and service load. If you say service load, it means ASD. It means that you have used this load combination. You're just adding the dead load to the live load and so forth. Okay? But if you say ultimate load, it means that you have used this load factors to figure out the maximum load that the structure member is going to be supporting. Again, a reminder, if you are sizing the footing, you do ASD, which means that you use service load. When you're doing here the reinforcing, you need to do ultimate load. So the good thing it says here, here's the ultimate load. So, okay. Now, how much is the pressure below the footing? So I'm going to say the pressure, according to what you said here, this pressure is going to be Q equals to P divided by A at the surface level. You say, okay, now, but I'd like to design the concrete footing in terms of reinforcing inside it. So if you're talking about reinforcing, you need to put it on the ultimate level. What is the ultimate level? Like ultimate loads, like a trend design. And the good thing, it was given to me here. It was given to me again. If you feel here that I'm repeating, I'm intending here to repeat the information because a question is going to come and say, why didn't you do it that way? So this here, ultimate load, 680. which means I can have also ultimate pressure, ultimate soil pressure. I can have surface soil pressure and ultimate soil pressure. The surface soil pressure is used to size the footing, like length by width. The ultimate soil pressure is going to be used to figure out the reinforcing and check the shear if needed. So we're going to say, okay. Here's Q ultimate. This is the one that I'm after. What's Q ultimate? It's going to be equal to P ultimate divided by the contact area between the footing to the soil. How much is P ultimate? 680, as it says here, 680. And the footing dimensions is going to be 8.6 by 8.6, 8.5 by 8.5. So I'm going to say, here we go. Q ultimate, which means soil pressure under this footing. Here's the plan of the footing, 8.5 feet by 8.5 feet. Forget about this hatching for a second. And here's the column, 24 by 24. Ultimate pressure is going to be equal to 680 divided by 8.5 squared, the contact area. And with that, you have 9.41 kip per square foot. This is going to be 9,410 pound per square foot. But this is at the ultimate level, not the surface level. Are you guys with me? Any questions? Yes, we're good.
Professor, so
Yes.
this value is used to help us calculate the reinforcement in the footing.
Yes.
Is that right?
Yeah, because now we're doing member design. You remember we're doing here footing size. We have two issues. Footing size is going to be surface, right?
Yes.
Footing reinforcing and shear is going to be ultimate. Like in here, it's going to be trend design. It's going to be with this Q ultimate. And in this problem here, they said, well, now you have the size of the footing, just give us the reinforcing. I said, okay, this is good. Now, how does this footing look like in the elevation? I'm going to say in elevation, it looks like this. Here's the footing, right? And where's the column? I'm going to say, here's the column. So everybody follow me here? Column is 24 by 24, and here's the footing. Yes or no? Are we clear?
Yep.
Should we also know how thick that is?
The footing?
Yes.
Yeah, very good question. It says here, 30 inch, 2 feet and 6 inch deep. So we have here the width. But you see the way I have drawn it here, I'm just aligned with the column and the footing with the footing, right? So this makes sense. This will be the elevation of our footing with the column, all right? And again, how much is the thickness? It says here 30 inches. Where do I come up with 30 inches? It says here 2 feet and 6 inches. 24 plus 6 is going to be 30 inches. Now, where is the column load? I'm going to say column load is going to be coming like this, right? It's going to be an axial load. It's going to be coming like this. Now, where it goes? It goes to the soil. The soil is going to be right here. So you're going to see here the soil pressure is going to be coming this way. This makes sense to you guys? Right? Throughout the width of the footing. Yes or no?
Yes.
Just gonna end up with just here. But you know it's going to be throughout the width of the footing. Now, where is the tension side? And when any deflection or deformation is going to happen to the footing, which side is going to happen? You're going to say tension side is going to be at the bottom because you're pushing this up, right? You're pushing this up. It's true that this is here the axial load coming. This is going to be the applied load, and this is going to be like a reaction. But you know what? This reaction is pushing this footing to bend it this way, right? It wants to bend up. So the bottom reinforcing is going to be the tension reinforcing, right? Bottom reinforcing is going to be from here to there, correct? Because it's going to be exposed to tension. Compression is going to be in the top. Tension is going to be at the bottom because you're pushing this up like this. The moment is going to be acting this way. So, okay, good. Now this is going to be the bottom reinforcing. Now, how much cover should I use? Concrete cover. Yes, say, well, concrete cover is going to be an issue, and here's the reason. In columns, I used 1.5 inches, right? In beams, I use 2 inches, sometimes 1.5, sometimes 2.5 inches max. In foundation, I'm going to be using here 3 inches. So I'm going to say in foundation, cover for foundation, for footings, is going to be how much? 3 inches minimum. Why? Because it's going to be exposed to soil. Soil is going to be right here. So you'd like to have good protection for the rebars from the soil. So I'm going to make it here 3 inches. You're going to say, is that it? I mean, how about the reinforcing bars? And are you going to be providing reinforcing bars only in one direction? So let's here look at the plan view. It means in the plan view, this rebar that you're looking here at, I can draw it this way on the footing. So I'm going to say, here's the rebar in this direction, right? Let's say, here's the rebar. It's going to be running this way, correct? Which is this rebar. Just show it in the plan. And the rebar running in the other direction, I can also draw it like this. I'm going to say, now here's the rebar running perpendicular to it at the bottom also. Correct? How would I see the 3 bars here running in this direction? I'm going to say, let's zoom in, and it's going to look like circles, right? It's going to be very small circles. It's going to be like this. I can just put it here on the top, and they can run it throughout all of this width. So we're going to have another rebar here, right? Have another rebar here, and so on, correct? All the way to the end. Now, do you want to see an actual picture of this rebars? I'm going to just take you back here to this picture. You see the rebars, they run in both directions, in the top and the bottom. You see here this footing? You see the rebars running in both directions. And if you see here, some rebars is going to be right below the other rebar. So this rebar is giving the top, and this rebar is giving the bottom right below it. So we're going to look here at this now, my drawing, try to understand what's happening. So I'm going to say, in plan view, I just showed it like 2 lines like this, right? But it's going to be at the bottom. And in the elevation, I can also draw it this way. Now I need to figure out the depth D, not H. Total thickness is going to be 30 inches. I'm going to be subtracting here 3 inches for the cover. And this rebar size, I'm going to say it could be number 7, number 8, like what I'm here looking at, 6, 7, sometimes also it's going to be number 8. So maybe the diameter for one rebar is going to be 1 inch. But now, where's depth is going to be at? Someone's going to say depth is going to be from the bottom layer of the rebars, which means from here. Someone else is going to be saying from here. I said, well, it seemed that we need to design here for both directions, and maybe an average value will take care of it, like an average value in the mid-height. So in this example, an average value of just 1 inch was considered. This is why it says here for the depth is going to be equal to 30 inch, total thickness, subtracting the cover, subtracting 1 inch for the rebar size. I said, okay, now the depth is going to be 26 inch. What is this depth? Distance from the rebar to the top compression of the concrete. Why do I need to design it in both directions? This is going to be the question. Why would you need to have reinforcing in both directions? Because when you think here about this footing and you start to put pressure in the middle, it's true that this side maybe wants to lift up. This side means this side here, right? It wants to lift up. And this side also wants to lift up. This when you cut a section through here, right? This column and this footing means that I'm going to be cutting a section through this and looking this way as an elevation. But I'm going to say, if you also look at a section in this direction, so we're going to say, let's cut here a section in this way, and look from this side. We're going to say, let's look here from this side. You're going to be seeing a similar column and similar footing. It's going to be exactly the same, which means this side of the footing and this side of the footing wants also to lift up. Meaning, this rebar that I'm showing here as circles, this rebars will also need to be designed for the same force that you have designed the other rebars for. So actually, your design, when you're doing a design here, your design is going to work for both rebars, for both directions. Okay? Okay, good. Now, where's the critical section for a moment? Where does it happen? I said, well, the word here, critical section, I said, I heard it before, but it was mainly for shear, but also for fracture. A very simple question to you. If I have simply supported beam, right? And exposed to uniform load, where is the maximum moment? Can someone help me with this? Maximum moment happens?
In the middle?
Right in the middle. So actually, this is going to be the critical section for moment, correct? In this beam. But how about here in my footing? Where is the critical section? You say, someone's gonna say critical section, let's just take it here at the middle, because this now acts as a cantilever. Cantilever with uniform load. So we're gonna say cantilever with uniform load. Do you have an equation for the moment on it? You can say yes. If you haven't seen it before, it is so simple. And the equation says M equals, generally speaking, for any cantilever, WL squared divided by, can someone help me with this? You can say WL squared divided by what?
8.
2. It's going to be divided by 2 for cantilever.
Oh.
Simply support is going to be W squared divided by 8, because they have here 2 supports. Now this works as a cantilever. Now where is L that I need to use here for my cantilever? I'm going to say cantilever is going to be the distance from here, I'm going to say only to here, because my section is going to be right at the face of the column. Let's say this here, the face of the column, I'm going to be taking a section here, is going to give me the maximum moment that may happen on the footing. But someone's going to say, why don't you take the section right here in the middle of the column? You're going to have the longer distance or arm, right? You're going to have the longer cantilever. You're going to say, because look at the depth. How much is the depth here of the footing? Say, wow. Now, when you take this section and you have the column right above it, this you can say technically here's the depth of the footing. It's not going to be 30 inches. It's going to be maybe 10 feet or 20 feet or 30 feet. It's going to be the total height of the column. So it doesn't make any sense to take a section right in the center. Going to be taking a section. It's going to be either here or here. And this is going to be the cantilever length from both sides, because this column is going to be right in the middle. This is why I'm talking about critical section for a moment is going to be at the face of the support. What support? The column. We call it a support. So in this case, critical section is going to be right at the face of this support, which means right here, right? It's going to be critical section for the moment. The maximum moment happens here. And the question is, how much is this X distance? This is going to be now the cantilever length. X is going to be equal to 8.5. You subtract 2 feet out of it, and then you divide by 2, because this is going to be X equal to the other X. It says here, X equals 8.5 divided by 2, minus the 2 feet. This is going to be 24 divided by 12. It's going to be 2 divided by 2. It's going to be a foot. This is going to be 3.25. So whether you take the total width or length of the footing, you subtract the column, divide by 2, or you say, let's take here half of this. So it's going to be half of 8.5, subtracting the 1/2 of the column length, which means a foot. You're going to end up with 3.25 feet. So now I have the cantilever length. Questions? Christina?
Excuse me.
Yeah.
For calculating the D.
Yeah.
Okay, I understand the 3 for the cover, but that 1 which you subtracted actually is going to be fixed for all the things, or it depends on?
Well, usually what's going to happen, you need to design it in both directions. Once you're going to design it for this way, and once you're going to design for this way, right?
Yes.
And for each direction, you're going to have different depth.
Yes.
Does that make sense?
Yes.
So if someone would like to go into a detailed analysis, he's going to be taking 30 inches minus 3 inches, and then he's going to say, let's subtract here 1/2 inch, correct?
Mhm.
To get to the first layer. So if you say this rebar, he's going to be number 8, to get to half of it, it's going to be minus 1/2 inch. And with that, you end up with 26.5. And when you like to design for the rebars running in this direction, north-south direction, you need to subtract 1.5 inch. Does it make sense? This 1.5 inch?
Yes.
1 inch is going to be for this rebar diameter, and then 1/2 inch to the center of this rebar. Some people would feel that this is just too much, because at the end, I'm going to set this amount of rebar in this direction to be the same as this. I don't want to change it. In construction, you cannot have the same footing size or dimensions, right? In both directions, you're going to have different reinforcing. People's going to say, what is going on? It doesn't make sense. So you need to set them equal to each other anyways. So going to an average value in the middle is okay, design-wise.
So I'm talking about initially you assume that they're going to be number 8 rebars.
Why do you assume number 8 rebars? Yes,
Because-
at the beginning, yes. It's just an assumption. It's gonna be a 1-inch rebar.
So
Yes.
is it, this is a regular procedure to just assuming that
For foundation,
Okay.
usually it depends on the size. But if I have here 8.5 feet, most likely I'm gonna go to number 7 or number 8. Yes.
oh, so it's actually, we have to, is it based on practice, no?
Yeah, this is just based on practice. But let's say that you're doing a design in one of this, problems or exam or whatever. I need to tell you exactly what size, what rebar size I want you to use. Otherwise, someone's gonna try number 4, someone's gonna try number 5, right? It's gonna have too many rebars. So I need to help a little bit and give you the proposed size.
So initially we assume it's going to be number 8, and then we have to check it if it is adequate or not.
Yes, at the end you need to check it. Yes,
Okay.
Yeah.
Thank you.
no problem. So what happened? Now I have the cantilever length, X. Now I need to figure out the moment at this section. So now how can I do the moment? I'm gonna say, well, I need to have the force. I have a total force that's acting right here in the middle, which is this force here. It's gonna be one big force. This force is gonna be equal to this pressure below the footing, below this shaded area, multiplied by the moment arm. And the moment arm in this case, from here to the section, is gonna be equal to X over to 1/2 of X. Why? Because this force here, it happens right in the middle, right? Which means you're gonna have your X over 2, and the force is gonna be right in the middle. And then you say, this force here multiplied by X over 2. So someone's gonna do here the pressure, entire pressure, multiplied by this area, contact area, find out the force, multiplied by X over 2, which is the same as this equation, by the way. So this equation is gonna be the same thing that I'm doing here. Now, M ultimate at this section is going to be equal to Q ultimate, which is the pressure from below the footing, times B. B is going to be the width. So in this case, I'm going to be calling this B, the width of the footing, times X squared divided by 2, which means W squared divided by 2. Now, where's W? W is going to be Q times B. So if you like, you can call this Q times B is going to be W, because this Q is going to be pound per square foot or kip per square foot. And once you multiply by B, is going to be kip per linear foot, which is the W that you are used to if you're doing cantilever analysis, the simple way that you know of. So first you do Q times B times X. So what do you do here? Q, which is the pressure, times B times X is going to give you this force. Here's Q times B times X. And then you multiply again by X over 2 to find out the moment. We run the analysis. We have 422.4 kip foot. So here's the moment at this section. Now you have the depth, you have the moment. Can you figure out the reinforcing? And here I have 4 reinforcing programs or alternatives. So I'm gonna say, here's my moment equation. This is the moment equation I know of. There is no compression reinforcing that I need to consider, right? So I'm gonna say, here's my moment equation. Phi man equals ASFY D minus A over 2. Do you have A? Do you have the value of A? I'm gonna say no, because I don't know the reinforcing yet. All what I have the ultimate moment and I have the depth, and I'm trying to come up with the reinforcing. So you say, okay, this is like the first round. You know, when you're doing the first round, you're trying to figure out how much reinforcing that you need to put there. So you say, okay, now you'd like M sub U to be equals to phi man. So I'm going to be setting here phi man equals to M sub U. This is something that we understand, because the worst case, when M sub U is going to be equal to phi M man, right? This is the way we write it down. Give me a second. Let me look for something here. A second. It's gonna help out. I just use this. So worst case, right? When M sub U is gonna be equal to phi man, you would like this phi man to be larger than, I'm gonna put here larger than, right? This is gonna be larger than, phi man is gonna be larger than or equal to M sub U. So worst case, if you just set them equal to each other. So I said, okay, let me take this out and put M sub U, because I have the numerical value for M sub U, 422.4. So exactly this is what happened. I took here AS out, right, on the other side, and then say it's gonna be equal to M sub U, and instead of phi man, right? This replaces this, and then divided by, don't forget the phi factor here is missing. Here's a typo in the slide. I'm gonna say here's gonna be the phi factor, right? So phi factor here is missing in this equation, needs to be there, right? It's gonna be phi times ASFY d minus A over 2. So I said, okay, let me take the equations, gonna be M sub U divided by phi Fy, here's the phi times Fy. And since I don't have A over 2, I'm gonna assume that d minus A over 2, this whole box is equal to how much? This term is equal to 90% of d. We went through this already very quick, but we didn't really spend time working on it with you guys. So I'm gonna say d minus A over 2, I'm gonna have an assumption for it, it's gonna be 90% of the depth d. Just an assumption. So I'm wondering, generally speaking, if I'd like here to assume in any other problem, what is the assumption of d minus A over 2? What is the range? I'm gonna say this here ranges from, I'm gonna say from 80% of depth to 0.95 of depth. This is a range. It depends on the actual value of A, which is based on the amount of steel. But now I'd like to start with something. I'd like to, because I don't know exactly how much reinforcing I need to add there, right? So I don't have the A value. So I can assume somewhere in between 80% of the depth to 95% of the depth instead of d minus over 2. Just the first assumption. So I said, let me just go here with 90% of d. Now in your analysis, if you decide here to use 85%, I cannot say this is wrong, right? It's just an assumption to come up with the amount of reinforcing. But it's very standard that we assume it's going to be 90% of d, and this is very common between structural engineers. Now I can run the numbers here and see how much is the AS required. Just to remind you, in the past we used to use this equation and AS was provided to us. Now I'm looking for AS. So AS based on this equation is going to be the AS required. In the past we used to see this AS provided in this phi mn, which is the strength of the beam. Now AS required based on this analysis is going to be 4 square inches roughly. You will notice here that M sub U has been multiplied by 12. You guys know what is this 12 for? Yes?
Change to inch.
Inches.
Yeah, very good. Thank you. This giving now kip inch. So I said here, let's try till number 7. How much is till number 7? A is provided now because now it's going to be try, which means consider this to be the provided amount. So the provided is going to be 6 square inches. Is this more than 4 square inches? You can say yes. It looks good. Now what I'm doing here, look at what I'm trying to do. Now I'm trying to find out the actual phi man. Now I need to do the actual analysis, the analysis that I used to do, which means I need also here to find the phi factor, right? I need to find A, and of course here I need to find C. So I'm gonna say here, need to find C lowercase, right? Or the strain in the steel. You remember the strain in the steel that you need to find it out, and then you need also to say that this is gonna be more than 0.005, right? Why does it need to be more than 0.005? To be sure that phi factor is gonna be 0.9. If you guys remember this chart, so this is exactly what I need to do. So I didn't show it here, but I have done it. I have done it in my analysis. So I'm gonna say this here needs to be included. Don't forget it. If you're doing any analysis in this course, you need to provide the C factor or calculate the strain in the steel and provide a means or you provide a way to confirm that phi factor is gonna be equal to 0.9 in this case. So I'm not gonna be going through this. I'm gonna say, you know what, here's a, you know how to do now the moment equation, phi factor, tension force, d minus A over 2, and of course divide by 12, and here's the phi man that you have. So you have a resistance of 683 kfoot versus demand of 422. Now you came up here with the amount of reinforcing that you need for this footing. So this exercise or this example, it is actually about understanding the meaning of the bottom reinforcing in a pad like this with some given loads. So here again in this example, I have the ultimate load, and I have the concrete strength, and I have the footing size. I don't have the reinforcing. I'm trying here to come up with the first estimate for the reinforcing. I'm just trying here to wrap it up and go through it again. So what I did, I was able to find out the ultimate pressure below the footing, and then find out the critical section for the moment, or the flexure, if you like, is going to be in this direction or it's going to be in this direction. They're the same because I have here square footing. And then after that, I need to figure out the moment at this critical section, run my first estimate for the amount of reinforcing bars. And once I have this needed or required cross-section area for the steel, I can try one of these options if I have a few options provided to me. So I'm just going to be trying this number and then find the actual Feynman for it, compare it with M sub U. And this kind of exactly what we do if we'd like to design a footing. So if you like to design a footing or a pad like this is exactly what we need to do. I'm walking you through the actual steps that we do. You have this rebar. In a second, with your calculator, you find out the amount of rebars or the needed, and then you throw something there, and then you start to find out Feynman. In previous lectures, usually, I give you the reinforcing, because I'm just assuming here that you don't really need to start from scratch, like what we do in design. Because at the beginning, you need to learn how to find out Feynman. It is not how to come up with the estimate. Now, this can be the time to come up with the estimate of the rebars, and then change it if needed. You can change this rebars if you don't like this number. If you find out that this gap, for example, is too much, and there's another option of reducing number of rebars. So someone's going to say, can I use 9 number 7 or 8 number 7? You can say, yes, you can. Why not? You can reduce, you can take out one rebar, because I feel here that you have enough room. When you have Feynman capacity of 683 and the demand 422, you say you still can. But I'm looking here at the options. That was not available to me. So I'm going to say, okay, let me just stay here with cell number 7. That was a good option. I'm going to stay with it. Any questions?
We had to find the spacing between the rebars to
Yes.
confirm that it fits
Yes,
within
absolutely. The spacing is going to be important, but it's going to be coming later. It's going to be coming. But for here, the purpose of this example here is to show you the meaning of a pad, critical section, rebars in both directions, finding out M sub U, estimating the amount of rebars, and then confirming that this rebars is okay for me. But there's more checks. There's also minimum reinforcement. Did we talk here about minimum reinforcement for foundation? Is it going to be the same as beams? I'm going to say no. Slabs and footing is going to be different animal and has different minimum reinforcement requirements. And we're going to be going through this at the time. All right.
Excuse me.
Yes.
Why we don't actually from the beginning assume that the steel is in that tensional section?
Tensional section. What is a tension section?
Tension control section. I mean, the ES equals to 0.005. From the beginning.
This is what we did. This is why I have here. Very good question.
Yeah, instead
that was our assumption.
I know, but instead of actually putting D minus A over 2 to 0.9 D, we could, if we initially assume that steel is 0.005, then we can easily calculate the C with that similar triangle, and then.
But this is gonna take time. I want to do this quick. Okay. This is what we usually do. I'm showing the actual what we do. I mean, this is the reality. With just a calculator like this, right? In a second. And actually, when we do this, we call this 54K sign. People are just used to it. Then you say, take the moment, divide, multiply by 12, divide by 54, divide by 9, another 0.9, and then just take a depth. And in this case, we just take a depth of 26. Some people would say, let me just take the depth here of, let's say, 30 inches. You're going to say, it does make sense. Where's the cover? Where's the rebar size, right? Where is this discussion? Say, don't worry about it. I'm going to pick a little bit more rebars to cover all of these issues. So, and then he's going to tell you, just, I want you to do this. Don't worry about what I'm doing here. So this is something that we do for quick, based on experience, right? So some people just like to do it quick. They don't really care about the details of these calculations. You want to come up with the first estimate of rebars. So I'm taking here the same footing that we worked with. I'd like to check the shear, like beams. If you do a beam, you have flexure check and you have also shear check. So I'm gonna say, okay, now where's the critical section for shear? Critical section for moment was right at the face of the column. And I understand this because you cannot really take it at the middle of the column. Take at the middle of the column is gonna be no sense. Why? Because the depth of the footing is not gonna be just stopping here, it's gonna be extended to the full height of the column. So this, if you have two-story building, 14 foot each, you're gonna have 28 feet for the depth. You don't need any reinforcement. So here's the critical section for moment. Critical section for shear usually says gonna be a D distance from face of support. You guys remember this issue? D distance or no?
Yes.
Okay, let me put it from the shear design. We say you're gonna be going here D distance from face of support, and with that you're gonna be at the critical section. So great. Same thing here. Where's D distance from face of support? Let me go back here. D distance means gonna be coming from this column. Is gonna be from here. Gonna be taken from here. Go D distance like this. See this? Now where's the critical section? Critical section is gonna be right here. Gonna be drawing here vertical lines. Gonna be right here, right? Because now the distance from this new line or new section all the way to the face of the column is gonna be equal to D, right? You guys follow me in this? Distance from here to here is gonna be equal to, how much is this? Let's say this distance here is gonna be equal to D. So you're gonna be at D distance from face of support. So here's gonna be equal to D. Meaning, if I'd like here to go with another X for the cantilever length, this cantilever length is gonna be equal to what? Gonna be equal to X minus depth D, right? It's gonna be this guy minus this guy to give you this little bit of a cantilever. Now where's the cantilever? I'm gonna say, here's the new cantilever for the new section for shear. Let's give you this length. So okay, let's look at this. Here's a critical section for what? For moment, for flexion, face of support. I'm gonna go here D distance away from it because the picture that I just showed you. And this is gonna be now the critical section for shear at D distance away from face of support. Now, how much is this X? You can say, okay, we can run the analysis and X equals, I understand that from here to there is how much? 3¼ You subtract 26 divided by 12, which means depth. So this section here, or this term, is gonna be the depth. This one here is gonna be this depth. Okay, how about 3¼ 3¼ is gonna be this distance, and we calculated out in the previous exam. I can show it to you just to confirm, so that you guys are not lost. Here's X was equal to 3¼ Again, reduce it by a depth of D. So okay, here we go. It's gonna be a foot. Now what do? Now you need to find out the shear. You have all of this shaded areas gonna be loaded to the pressure that wants to go up. And Q is gonna be the same. Q is gonna be 941 from the previous example. So I have here the pressure, 9.41. You take it, multiply by 1.8, multiply by the width, 8.5. And this is exactly what we're doing. 941, the pressure, times 8.5, which is this width, multiplied by 1.08, which means this X distance. And with that, you have a shear of 86.65. So what do? Just take the shear. You find out PVN. You can say, do you have here any like ties? Do we provide ties in here in this case? You say no. Look at the reinforcement. Just bottom reinforcement. Even in this problem, I don't have here any top reinforcement. Some cases, you're going to be able to put top reinforcing, but in this example, there is no top reinforcing, there is no ties, which means shear strength is going to be provided only by concrete. So the equation now becomes much simpler. Look at this equation. Here's the equation for the shear. PVN equals phi, which is 0.75, area of the concrete times 2 square root of F prime C. So I understand this. Square root of F prime C times 2. You guys know where is this coming from. Let's give you this guy. Times 2. Phi factor, 0.75. The question is, where is this area coming from? This AC. Where is the area exposed here to shear? I'm going to take you back. I'm going to say, if you cut this section here, right? If you cut the section right here, what are you cutting through? Depth D. And where's the width that you're cutting through? I'm going to say you're cutting through this width. So the area exposed to shear, again, if you're cutting a section here, it's going to be equal to the depth multiplied by the width, 8.5 feet. How much was the depth? Anyone recalls?
2.5 feet.
26 inches, the depth, effective depth. Therefore, now the cross-section area exposed to shear is going to be 8.5 times 12. It's going to be the width in inches multiplied by 26, which is the depth. And this is going to be the area here exposed to shear. Look at the strength, 217. Very high strength compared to what? To 86 kips. So actually this footing is good. According to this given information, I was able to put the reinforcing and do a check on the shear demand. So I guess you guys now understand how we handle foundation. It's going to be very similar to a beam in terms of checking of the moment and the reinforcing, and also check on the shear at one section. But this is not the only thing. We have more things to come. Because what I want you to think about, what happened if this concrete footing is very thin? So I'm going to be taking this, going to be taking this box, going to be taking this guy here, going to be taking the 3 elements, just going to be drawing it here for you. So, okay. Now, if this is going to be very small, just happened that I put a very small section. What are the mode of failures? Expected mode of failure. I'm going to say, when it comes to expected mode of failure, you can have reinforcing failure, right? You can have shear failure. Anything else beside that? If this concrete pad is going to be very small, I'm going to say with this high load, I can have just punching through the footing. And you can think about it, if you have a piece of paper here, right? And then you have this paper, and then all of a sudden you put high force. What do? What are you doing here? You are punching through the piece of paper. Same thing, you are punching here through the footing. So it may happen that you may punch through the footing. So you need to check punching. So we have something new here that we call punch and shear check that you need to do. So in beams, we do moment check, shear check. We call this one-way shear or regular shear. In foundation, we do flexure check, like this example, right? Moment check. We do one-way shear check, which is this one. And also we do shear check, punching shear check, which we call also two-way shear. So here we go. Now we're going to start here the punching shear check, which is also two-way shear. Why two-way shear? Because look what happened. This may happen in extended concrete slab and also may happen in a mat foundation. This can be here a mat foundation, like extended footing. It also can happen in just a footing. So look at this. Here's a plan, and here's a column. The shaded area here's going to be the column. And look at this. It's going to be now critical section for punching shear. When this column here wants to penetrate through the slab, it's going to be going through this dashed line. Don't worry about this dashed line here. Just figure out the tributary width. You say, okay. Look for punching failure. What may happen in punching failure? Look at this. You see what happened? The column is just penetrating through this concrete slab. But guess what? It's not going to be just the column. The column is going to be taking a piece with it. This is why we have the critical section for punching shear is going to be different from the face of the column. Same thing here. If I may make this closer to you. The picture is not that great, but look at this. Here's the mode of failure. When each column is going to be failing, or the slab, look, here's the slab. This slab used to be here at this level. So what happened? It just collapsed. Why? Because of punching shear. The slab was thin, and there's no enough check on the punching shear between the slab and between this column and this slab column connection. And this is the reason that just the slab collapsed this way. Just too bad. Look at this. Here's one close picture. Another one. This is like an edge column, right? At the edge of the slab. This one here is going to be like interior column. Just too bad when you look at stuff like this. Look at the slab. Slab used to be here. Now where it is at? It's right here. It's at the bottom level. Just collapsed. And guess what happened to the cars in between? You just squeezed. They're gone.
Professor, so
Yes.
what's kind of like the procedure if we have already like precasted everything, it's already built? Is there a way of reinforcing?
Yeah.
Yep.
Yeah. I've done a project like this. Yes.
Mm-hmm.
We go below the concrete slab, and then we start to add some mechanical like connectors, channels, and stuff. On the top also you can add layers of FRP. So
Oh,
there's a way to fix
fiber.
it. Yeah.
Okay.
Yeah. So there's a way to fix it. You do it from the top and also from the bottom. But the one from the bottom is really important. That you really need to do something from the bottom,
Mhm.
not just FRP. I've done a project like this. Yes. Yeah. I said, okay. Now, how would you recognize cracks like this? And how would you call this to be a punching shear crack? And here's one case. You take out all the flooring, right? And then you look at the concrete slab. Now, once you get to the column, if you are walking, even without removing the floor, the carpet, you just walk on it, you feel that this kind of high. You start to go away from it 2-3 feet, it's gonna be kind of sloping, and then you feel here that something is wrong. And then after that, just sloping, because the entire slab is coming down. And look at here. After we have taken the carpet, we start to clean all of this, right? Look at this. At the beginning, of course, that was just cracks, but you need to chip it out, right? Chip all of this loose concrete, clean it. Now it is ready to be maintained and to be repaired, right? So this is the expected type of cracks. If you see the crack here is going to be only in one direction, this is not punch and shear. This could be shear crack or maybe flexure crack. But if you see it like around the column in certain ways, then you know that this is going to be here punch and shear. It needs to be fixed in a certain way. Here's the testing that we have done in the lab. That was, we were trying here to test the punching check or the punching shear. So here's the column. You have a piece going down, another piece going up, and then we start to apply load from outside, and here's the resistance, and guess what's gonna happen? Here's a crack, expected cracks. So I guess now if you're walking in an open concrete slab, it's in a parking structure, and you see something like this, you know what type of crack is this, and certainly you're gonna be staying away from it, right? Here's a slide showing why the critical section and this type of things. So I guess I'm gonna stop at this point. I let you guys go. If you have any questions, please see me at the office hour meeting. You have a good night.
Thank you,
Professor, would
Professor.
you mind? Oh, go ahead.
I just said thank you.
Oh, thank you, David. Thank you. I guess someone joined the meeting after. Someone joined the class. Was it Carlos?
Yes, I'm here.
Yeah.
Thank you.
Alex?
Would you mind going back to the other drawing with the chip?
Yes. Just give me a second. Let me finish this if you don't mind.
Not a problem.
Amin is not here. And Alexander. Okay, so I'm done with this business. Yes, I'm here.
So would you mind going back to the other slide? I think it was the one before this. So right here, it's because of the punching, but is it all is the reason why the rebar is being exposed? Is it also because perhaps the rebar wasn't set correctly? Because I believe you mentioned before, if we don't have the ties down correctly, the rebar can like
this
float
is just a
up.
slab. There's no beam. But look at this. Look what happened. Once you start to push down, look what happened. You're gonna have cracks like this, and the rebar is gonna be exposed. So this is exactly what happened. Now, when this is cracked, what we have done here, when this is cracked, right, we start to clean this area because the concrete is apart, right? It's pieces. So you need to chip it and clean it. All the loose concrete, you need to take it out.
So how would you reinforce it from the bottom? Because you mentioned the RFP. So would you like
steel members here? You need to provide steel members in both directions, like channels and things like this. And you need to design to take the force coming from the slab going to the column. You need to transfer it through this channels, and then you need to anchor it to the column. There's some calculations that you need to do. Yeah.
All right. Well, thank you so much.
Thank you. All right.
Have a nice day. Bye.
You too.